Time for us to do some problems with practice involving motion and also taking antiderivatives of vector-valued functions. As always, it's important to do practice because practice is how we get better. We don't get better by not practicing, like any skill in life. If you want to learn to cook, you need to cook. You want to learn to calculus, you calculus. And so that means doing problems. If you're following along with the video, make use of the pause button. See a problem you like? Pause and see what you can do on your own. And if you ever need help, you can unpause me, and I'll be there to lend a hand. Well, let's begin. Our first problem. Find the osculating plane to the following curve at time t equals 0. Now remember, what is the osculating plane? So the osculating plane is a plane that has three pieces of information. It contains the point, in other words, r at 0. It contains the motion, in other words, the velocity r prime is 0, and it contains acceleration, in other words, r double prime is 0. So that's great. Now how do we actually find our osculating plane? Well, the point is a point. Okay, so this would give us our point. Now, the other two pieces are vectors, because we think of motion as a vector. It has a direction and a magnitude. Acceleration is a vector, it has a direction and a magnitude. So there are two vectors that we want to be in the plane, because osculating plane should contain them. So I now have two vectors in the plane. So we do what we always do if we have two vectors in the plane. We cross them, and this is our normal to the plane. And then we have our normal to our plane. We have our point. Life is good, and we can write down our answer. So let's start by taking our derivatives. So we didn't need to take the first derivative and our second derivative. So what do we have? Well, we'll write all of our functions down. So r of t, e to the 2t minus 3t, comma, sine of 2t minus cosine t, comma, t squared minus 2t plus 4. Okay, that's just a function. R prime of t, well, we take the derivative entry by entry, term by term. So that would be 2e to the 2t minus 3, comma, 2 cosine 2t plus sine t, comma, and 2t minus 2. Oops, 2. And there we go. Okay, so we took the derivative entry by entry. So for example, the 2 came down by the chain rule, and that's what happened here with this 2 as well. And of course we need the second derivative, r double prime. So r double prime of t, 4e to the 2t, that goes away, minus 4 sine of 2t. This is because I have a 2 and another 2 by the chain rule. And then plus cosine of t and 2. Okay, well, now evaluate. What do we get? Well, we get r of 0. Well, nice thing is 0 is a good number to work with. 1 minus 0. 1. 0 minus 1. Negative 1. 0 and 0 and 4. 4. R prime is 0. What is that going to be? 2 minus 3. Negative 1. 2 plus 0. 2. 0 minus 2. Minus 2. R double prime 0 will be 4. And 0 plus 1. And 2. All right, so we're doing great. Now we have our r prime and our r double prime. We know by crossing them we get our normal. So our next step, let's cross and see what we get. So we have I, j, k. Minus 1, 2, minus 2, 4, 1, 2. So I times 2 times 2, 4i, j times minus 2 times 4, minus 8j, k times minus 1 times 1, minus k. Go the other direction. 4 and 2 and k, that's 8k, but we subtract. So minus 8k. Then 1 minus 2 times I, that's minus 2i, but we're subtracting, so it becomes really a plus 2i. And then 2 minus 1j, that's minus 2j, but we're subtracting, so it really becomes a plus 2j, which makes this 6, comma, minus 6, comma, minus 9. Now, we should always check our work, because the one time you don't check is when you do it wrong. So we check by taking our dot product. Minus 6, minus 12, plus 18, 0. 24, minus 6, minus 18, 0. So that's great. That means that we have our correct cross product. So we have our normal. Now, notice we can pull out a common factor of 3. So I can use 2, negative 3. And this is probably simpler to work with. So that goes back to the idea, like, there's not the normal, but rather there's many normals, so we just need to find one of them. We can always scale our result to make things easier to work with. So for instance, we can scale it so there's no common factors. So, all right, there we go. Now we have our normal, we have our point, and we're almost done. We're almost done with this problem. What do we do? Well, these will represent our coefficients. So 2x minus 2y minus 3z equals. Now we use the point here. So do a little bit of computation when we plug in our values. 2 times 1 is 2. Minus 2 times minus 1 will become plus 2. And then minus 3 times 4 will be minus 12, which would give us 2 plus 2 minus 12 would be negative 8. Okay, so that says that we're going to get 2x minus 2y minus 3z is negative 8. And that is our plane, our osculating plane, our plane that contains our point, contains our motion, and it contains our acceleration. Beautiful, beautiful. All right, well, there we go. Good, good. Well, on to some more problems, right? Of course. We should always be looking ahead, looking forward to more problems to work on. So, the next problem. Find the integral from 0 to 1 of a half t plus 2, comma, e to the t, comma, cosine t dt. So in other words, we're integrating a vector value function. Now this is a definite integral. Now how do we do definite integrals? Well, the answer is one entry at a time. That's what we always do. One entry at a time. That's the way vector valued functions work. So it's the same ideas that we had in Calc 1. We just do it 3 times, once for each entry. So for instance here, we can say, look, this is really the integral from 0 to 1 of a half t plus 2 dt, comma, integral 0 to 1 of e to the t dt, comma, integral 0 to 1 of cosine of t dt. Well, okay, what's that? That's integral of a half t plus 2 would be 1/4 t squared plus 2t. Evaluate from 0 to 1. Integral of e to the t, evaluate 0 to 1. Integral of cosine, positive sine, and evaluate 0 to 1. And we plug it in, plug in 1, 1/4 plus 2. Well, 9/4, because 2 is 8/4. And then when you plug in 0, you get 0, so 9/4, comma. Now here, e to the 1 minus e to the 0. Well, e to the 1 is e to the 0 is 1. Sine of 1. Now, sine of 1 we can write as sine of 1. Yeah, it doesn't really simplify. Well, not everything has to. Sine of 0 does. Sine of 0 is 0. And we're done. Now, you might be saying, well, hold on. Do we have to do it that way? In other words, do we have to really say what's happening in every individual entry? And the answer is no. You can certainly do the following. An alternative way to write it is to say, look, just do the antiderivative of every entry. So you could say 1/4 t squared plus 2t e to the t sine t, and then evaluate from 0 to 1. And then, of course, you still end up at the same place. And so you just, do you want to do it entry by entry, or do you just want to say we'll do it all at once? Just make sure you put the evaluation symbol somewhere to make sure everything gets evaluated, everything gets accounted for, and you're good. Life is great. All right, well, good. Let's keep going. So, a particle has acceleration, and it's this function, 3 e to the t 1, 12t squared minus 4. And we know at time 0, the particle is at a given location, 1, 0, minus 1. And at time 1, it's at another location, minus 2, a half, 0. Where is it at time 2? So we know where it's at time 0. We know where it's at time 1. Where is it at time 2? Okay, so let's think about it. Now, we're asking about position, and we're given acceleration, which means we've got to take 2 steps, right? So acceleration to velocity to position. That's 2 steps. So let's begin. So acceleration is 3 e to the t 1, 12t squared minus 4. Okay, first step, take an antiderivative. So velocity, it's the integral of this function. Oftentimes we won't write this part down, but just emphasizing what's going on. And we do the antiderivative term by term. So it would be 3 e to the t plus some constant c. Then t plus another constant, we'll write d, because they're different constants. And then, 12t squared, antiderivative of that, well, that would be 4t cubed minus 4t plus another constant. Okay, and there we go. Now, that's velocity. Okay, so we took our first step. We need to take one more. Okay, so our next step is position, r of t. Okay, so again, we're just going to integrate our function. Now you might say, but wait a second, we don't know all these things. We don't know e, or d, or c. Are we allowed? And the answer is yes, you are. You are allowed. Just that as you integrate, you have to treat them like you would any other number, because they are a number. We just don't happen to know which exact number. So what do we get? Well, we'll get 3 e to the t. The integral of c will be c times t, right? It's a constant, so integral of a constant is the constant times your variable. And then a new constant, well, working our way up through the alphabet, looks like we're up to f. And then integral of t plus d, a half t squared plus d times t plus g. And then t to the 4th. And integral of minus 4t minus 2t squared. And the integral of e times t. And then h. Okay. We made it. We made it. Okay, so now we have a lot of things we don't know. So we can't plug in 2, because if we plugged in 2, our answer would involve all these constants, which we don't know what they are. That doesn't help us. What we have to know is we have to know what the constants are. To use that, we need to use information that we've been given. And we have been given information. We've been told something about where we are at time 0 and where we're at time 1. So let's use what we have at time 0. So we have our time at position 0. Sorry, our position at time 0. I had all the right words, just in a slightly different order. Okay, will be what? Well, according to this, it's at 1, 0, minus 1. Okay, so that's 1, 0, minus 1. Okay, now we plug 0 into here. What do we get? Well, we'll get 3, and then that'll be 0 plus f, and then we'll get a 0, 0, and g, and then we're going to get a 0, a 0, a 0, and h. It's so nice working with 0. You know, in math, we love 0. Oftentimes people are like, I hate 0. It reminds me of my bank account. No, 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 no. In math, we love 0 because it's so easy to work with. A lot of things simplify. Now, the key here is just to say, hey, entries match. So, for example, 1 is going to match with 3 plus f, 0 is going to match with g, and minus 1 is going to match with h, and so we can solve. So, for example, since 1 is 3 plus f, that tells us that f is negative 2. Since g has to match with 0, well, that's g is 0, and h has to be negative 1. Great. So we can update, and there we are. Now, that's one piece of information. We had a second piece of information, namely what's happening at time 2. Sorry, at time 1. Time 1. I got ahead of myself. Time 2 is what we're looking for. So, repeat the process. Plug in 1. Now, at time 1, the particle is at. See, the key word here is at. At is referring to location. So we know we're looking for location. So, minus 2, 1/2, 0 equals. Okay, so we plug in 1. 3e to the 1. Well, that's 3e. Then plus c minus 2. Oh, there's a lot there. Then we're going to get 1/2 plus d. All right. And then we're going to get 1 minus 2. And then there's going to be another minus 1. And then there's a plus e. So when we put it all together, there's a 1 minus 1 cancel. And so we left with minus 2 plus e. But again, we do our same pairing as we did before. So for example, minus 2 has to equal 3 times e plus c minus 2. Well, we see that tells us c has to be negative 3e to get things to work out. The 1/2 equals 1/2 plus d. Great, d has to equal 0. 0 has to equal negative 2 plus e, so that says e has to equal positive 2. So we can update again. So e is now positive 2, d is 0, so that's just out, and c is really minus 3e. So now we actually have our position function exactly. We've figured out all the constants. Since we have our position function at all times, certainly we can find our position at time 2. So the last thing for us to do is to plug in 2 and see what we get. So our position at time 2 will be r of 2. Well, that's going to be 3e squared, then minus 3e times 2. So actually it'll be minus 6e. There we go. Forgot that we're plugging that t. Okay, and then minus 2. Well, you can't really simplify. E squared and e's, they don't combine. 1/2 times 2 squared will become 2, and those are both gone because they're both 0. So 2. Then we have 2 to the 4th, 16, minus 2 times 2 squared, so that's minus 8. So 16 minus 8 plus 2 minus 1. Well, if you simplify, really, since you have minus 8 minus 1, that's really minus 9. And, whoop, it's not plus 2, it's plus 2t. Careful, careful. This is what happens when you're trying to compress all your notes. So 2 times 2 makes this a plus 4. So we have 16 plus 4 is 20. Minus 9 makes it 11. Okay. And there we go. That's where we're going to be at time 2. All right. Well, good. So the idea is simple, as long as you remember don't forget, there are t's here, and be careful. The process, you start with your function, you take antiderivatives. You might have to take more than one, and every time you take an antiderivative, you get constants. So in this case, we had to take two antiderivatives, which really meant we needed two pieces of information. So essentially, you should think every time I take an antiderivative, I need to have a piece of information somewhere for me to figure out what the right constants are. And so in our case, our information, where are we at times 0s and 1? Great, that was our two pieces, and that helped us figure out what all the constants needed to be. All right, well, I think we can do one more. So, last problem. Here we go. Let v of t be e to the minus t plus 1 to the minus 3 halves, and 1 over 1 plus t squared be the velocity of the particle, which at time t equals 0 is located at the point 1, 3, negative 2. Determine the location the particle moves to as time goes to infinity. So, okay, well, what do we have? We have velocity, we want position. So we need to take that step. All right, so we'll take our first step. So the step is, we're going to have our velocity, I'll write it down again for reference, e to the minus t, comma, t plus 1 to the minus 3 halves, comma, 1 over 1 plus t squared. So position, well, I was going to write p, but we use r. Our position, r of t, is found by integrating velocity. So we integrate term by term. So let's do it. The integral of e to the minus t is minus e to the minus t. And I'm going to put my constants at the end, just to show you a different way to mark your constants. Here, the integral of t plus 1 to the minus 3 halves, well, it'd be t plus 1 to the minus 1 half. You add 1, then you divide by the reciprocal, or sorry, multiply by the reciprocal, minus 2. Now, you might say, wait, what about the fact that there's a plus 1? Well, it turns out that if you just shift, like add a constant, you still do the same in antiderivative. You can do it by doing a substitution and working it all out, but a shift doesn't change the process. Now, 1 over 1 plus t squared, aha, that's a good one. We should know that one. It's arctangent. Now, there's a constant. Or really, we should say, because it's a vector-valued function, a constant vector. So we'll write it as c, d, e. Okay, so there's that constant that we need to figure out. Well, we know where we're at time 0. So we say, okay, we have at time 0, our position would be 1, 3, negative 2. We're just rewriting it as a vector, so it's compatible with how we write our function here, is equal to, okay, so plug it in. We're going to plug in 0. Minus e to the minus 0, minus 1. Minus 2 times 1 to the minus a half, minus 2. Arctangent of 0, 0. Okay, great. And then we have plus our constants, c, d, and e. Well, now to solve for c, d, e, you can subtract. So that says our vector c, d, e is equal to 1, 3, minus 2. Excuse me. Subtract minus 1, minus 2, 0. And that becomes 1 minus minus 1, 2. 3 minus minus 2, 5. Minus 2 minus 0, minus 2. All right, so there's our vector, and this is our constant. So this really says, look, this becomes 2, 5, negative 2. Now we say, great. What happens as time goes to infinity? Well, let's think about our pieces here. What does happen as time goes to infinity? The e to the minus t. Well, that's e to a large negative number. That's going to 0. Here, I have a big number, t plus 1, to a negative exponent. That's going to 0. Here, I have arctangent of t. That doesn't go to 0. Okay, so what happens to arctangent? Well, if you think about the graph of arctangent, which of course all of us sooner or later think about the graph of arctangent, it looks like this. And it has horizontal asymptotes. Now the horizontal asymptotes come from the vertical asymptotes of tangent, which means it's approaching pi halves. So this approaches pi halves. So what we have is as t goes to infinity, we have that r of t is going towards, well, 0, 0, pi halves, plus this vector, 2, 5, negative 2. Well, we put it together, and we'll get 2, 5, and pi halves minus 2. And there we go. That's it. That's our answer. So that's where our particle goes to as time goes to infinity. Really, this is the same kind of things that we did when we talked about things in Calculus 1. So it shouldn't feel so odd or unusual. If anything, it should feel, wow, this is really familiar. It feels just like we've done this before, because it's just like we've done this before. The only difference now is we have 3 slots to take care of. That's it. And so it's not so bad. We can handle this multivariable calculus stuff, no problem. A little bit of work, and we'll be in great shape. So keep it up, and we'll see you again in a future session.